Okay, great. So we're 2 minutes after the hour, so I think why don't we go ahead and get started. Welcome everybody to our IRSIG webinar for today. The IRSIG is the Infrared Science Interest Group. I will be moderating the webinar today. My name is Meredith McGregor. I'm one of the co-chairs of the IRSIG Leadership Council along with Mike Zemkoff, and outside of these duties, I'm an assistant professor at the University of Colorado Boulder. Before we get started, I wanted to sort of go over how this will work. I know we're all getting very familiar with Zoom meetings, but just a few logistics for how we run the webinars here. If you have questions for our speaker, and I hope you do, please type those questions into the chat window. If you don't already have that up on your screen, you can mouse to the bottom of your Zoom window and click on the button that says chat, and it will bring it up. Please submit questions as they come up during the talk. At the end of the talk, we will have a Q&A period. Generally, how we've been running those is any questions that I see in the chat window, I'll read them to our speaker, and then he can respond. If you very much want to ask your question, at the very end, we can possibly use the raise hand function and unmute people to ask questions directly to the speaker. You can also ask questions of the Leadership Council, those of us who are running the IRSIG. We'll wait until the very end of the hour to address any of those questions that come up, or if we run out of time, then we'll send you an email afterwards. You can also use the chat window again to report technical difficulties. If audio goes out or the internet connection is funky, please let us know. And the last relevant piece of information, and I realize I put the wrong link in here, I'll update that, is this webinar is recorded and will be posted to our website. But the link that I already typed in is our previous website. We just upgraded our kind of tech side of the IRSIG, and so we have a brand new website. So I'll post the new link for that during the talk. And with that, then it is my pleasure to introduce our speaker today, Mark Devlin. So Mark is currently a professor at the University of Pennsylvania, and he is going to be talking to us today, titled New Results from the Atomic Cosmology Telescope and New Prospects for Submillimeter Measurements of Polarized Dust. So with that, I'll let you take over, Mark.
Great. Well, thanks very much. Guys, I assume you know I'm going to be just sharing my screen and going through this Zoom style. Thanks for having me here today. It's always fun to, I'm just trying to figure out, we figured out how to do this. Let me see, spotlight, there we go. I'm going to be talking about, I do a number of things, but mainly a lot of cosmic microwave background research, and mostly recently on the Atomic Cosmology Telescope, although I do spend a lot of my time now on the Simons Observatory, which I'll give you an update at the end. But we recently had a fairly substantial data release, our data release 4, which has really taken things to a new level as far as I'm concerned in our understanding of the universe that we live in. So I'm going to take this from the top. This is a picture of the cosmic microwave background, not one that we made. This is from the Planck satellite, which shows a combination of temperature and polarization map over the entire sky. But we're going to start with, let me see, that doesn't work. Let me see. Click on the screen and maybe that works. There we go. We're going to start by talking about cosmology and how a cosmologist sees the universe. Of course, this is the Hubble Deep Field, which is a two-dimensional representation of our three-dimensional universe. And of course, the third dimension for us is time. But as a cosmologist, we're not interested in looking at the objects. We're looking at, trying to look at the universe as a system where we try to describe or understand where all the stuff is in the universe, that is, where it is in both space and time, and how is it organized? Does it have any kind of patterns that it follows, and then how did it get that way? And that is spurred by our understanding of what the evolution of the universe has looked like. This is a picture from the Planck team with some annotations by me showing the standard timeline from the Big Bang all the way up to the present day universe. But throughout that period, a lot's going on, where we go from instantaneous, a bunch of energy sitting there, to formation of particles, to the formation of plasma, to the formation of the cosmic background, and then forming the structures that we see today. And the general story here is that because we can study the universe as a function of time, we can understand not just how it evolved, but we can understand the physical parameters which govern how it evolves. And so understanding what the universe was like when the CMB was formed is great, but understanding what the universe is like at a whole multitude of times throughout that actually helps you to constrain the physical parameters which again govern the evolution as a function of time. And so the general theme behind my research is to try to pick away at that by not just looking at the CMB, but by looking at the structures in between the CMB and in the present day universe. So again, this is how the universe might have looked 13.4 billion years ago, when we had the decoupling of the cosmic from the cosmic microwave background. But the general idea is it's very smooth to one part in 10 to the fifth. So one piece of the universe is the same as the next piece of the universe, to a part in 100,000. And in a mere 13.4 billion years, we get this, which doesn't sound like a lot of time. I mean, it sounds like a lot of time, but really it isn't a lot of time. And so to get all the structure to form on scales ranging from our planet all the way up to hundreds and thousands of megaparsecs is something which takes a trick, and not trick, it just takes physics to make happen. And understanding the physics is what this is all about. How did it get from A to B, and what path did it follow to get between those 2 points? So again, looking at the universe back then, and you probably are aware the universe is formed mostly of the matter in the universe is mostly dark matter, and so this is just an old model of dark matter evolving over time. And what we're doing as a cosmologist is we're using, or at least astronomers and cosmologists, is while we're looking at these galaxies, we're really using them as tracers of where the dark matter actually is. And what I mean by that is this is now a non-evolving, this is just a current dark matter simulation of what the present day universe might be like. And you see this kind of cosmic web structure, and this video happens to be zooming into the largest mass structure in there, which is a giant cluster of galaxies. And what I take away from this image is that the universe is quite dynamic, in the sense that you have these streams of matter which are flowing in to these structures, and you create these big walls, and walls and voids of matter. And it really is fascinating how that evolves with time, but also how we can study it and learn more about the universe through the study of these things. So again, coming back to that similar image where we have time along the x-axis and scale along the y-axis, you have this universe which you want to study, and you can choose where to study it, and where you study will tell you different things. For example, if you want to study the very earliest universe, you're going to be looking at the inflationary epoch of the universe, which gravity is quantized, and that quantization of gravity waves propagates through the early universe and can leave an imprint on the cosmic microwave background. You might want to look at the neutrinos and light relics. They will leave an imprint on the CMB, but also they will affect the formation of structure again over cosmic time. And so the number of clusters that you might see, or the scales of structures, will change depending on the neutrino mass. And then finally, you might want to study the evolution of dark energy, which is understanding again this expansion history of the universe, but also looking at the lensing of the CMB, because these structures in here will actually affect what you see over here. You're looking through a distorted lens. I'll get back to that in a second. So it's really a rich a way of looking at there's many different paths for studying cosmology, studying the evolution of the universe, and everybody's turning all those knobs to try to figure out what we can. So taking a step back, this is a standard CMB temperature map. Happens to be an Act 1, and it's about 30 degrees on the side, ish, and it's a single denominator map, meaning that all the fluctuations you see in there are real. It looks like noise, but this is real. But really, the map itself doesn't tell the whole story, and you'll have to excuse my playing with PowerPoint. But essentially, while you're seeing these temperature fluctuations, there's really also these oscillations, or basically sound waves traveling through the CMB. It's in motion. In other words, if there's a hot spot, that means that the pressure is different than a cold spot. And that means density is different, and that's really pretty much a sound wave. And so when we look at this, we're also trying to understand not just the location of the matter, the temperature of the matter, but really the velocity of the matter during the surface of, at the surface of glass scattering, or in that volume that is the surface of glass scattering. And that becomes important in a second. So if I take a look at one of these, the map I showed you on the first graph, and I translate that, we produce these things called power spectra, which is essentially the power of the fluctuations on different angular scales, and that's multipoles, defined by multipoles here, but just to put it in perspective, around the first peak is about a degree. And so the first thing you would do is take a power spectrum of the temperature map, and that gives you something which we know very well right now, at least in the last decade. And you see these bumps and wiggles, which encode some of the cosmological parameters of the universe. Then you can take that map, or take that power spectrum and pull out from your model things like the baryon density, the cold dark matter density, the optical depth of ionization, and the spectral index of the primordial adiabatic fluctuations, for example. And all that comes from just looking at that power spectrum, because the models will, when you tune the models, it gives you a different set of parameters will fit the data differently. And so it's quite a constraining tool for understanding this. Using other derived parameters, you can also understand about the dark matter and matter density of the universe. So, you know, it's a very interesting way to learn about it, but we can go even further. This is now looking at this map right here, just to put this on perspective. Again, the same map I showed you before, and you might ask, well, how big is the map, right? And from what I've just told you, this is a temperature map. We know it peaks at a degree, and your eye can do a Fourier transform on this map. I mean, this separation here is going to be about a degree or ish. And so you can tell that this map is going to be something like, you know, 10 or 15 degrees on the side, just by looking at it. It's such high signal to noise. And that's really what's phenomenal about looking at some of these maps. From somebody like me who's old enough to have started out with just like 3 data points with really huge error bars measuring the temperature and anisotropy, to now getting these maps where you don't even have to run code on it to tell what the angles, you know, where the signal is. It's actually pretty phenomenal. So getting back to those the maps again, you can look at this the surface of glass scattering, and if the matter's in motion and you have these hot and cold spots, an electron sitting at the surface of glass scattering is going to see light coming from these several directions. But when we look at that photon from our direction, the electron from our direction, it's going to be shaken by these fields, and obviously the cold field and the hot field are going to be giving it different magnitudes. And when that happens, you actually wind up getting this Thomson scattering polarization effect. It's a scalar field, and it's essentially 100% predicted from the temperature map. So you have a temperature map, you should be able to predict what the polarization patterns will be because of this effect. And that produces its own power spectrum, which is called the E-mode power spectrum, which you see here. So we can go even further, and we can say, well, what else can happen at the surface of glass scattering? And there are those gravity waves which produce during inflation. And if they're propagating from the early universe and basically they're there during the surface of glass scattering, they're literally going to be stretching and contracting space. And that will have a similar effect to what we saw with the Thomson scattering, and it will produce an E-mode spectrum. But because it's a tensor field, it also produces what we call an E-mode, a B-mode spectrum, which is doesn't invert. You know, when you flip it, you don't get the same answer. And that's really important, because obviously we wouldn't be able to determine gravitational E-modes from the E-modes that we see from the normal temperature fluctuations. But these B-modes, they are going to be unique to this. And from that, you can find a B-mode power spectrum. And the important thing to see about this map is, as we did it, you know, this is back when I was in graduate school, we were going after just getting one data point on this peak. And now what you push it down by a factor of 100 and you get to the E mode, and then you have to go several more orders of magnitude down to get to B modes. And again, these numbers here are measured in nanokelvin temperature changes on the sky, and so the experiments have become exquisitely sensitive in order to be able to pull this off. So let's get back to that lensing thing. What happens after the photons are emitted? Everything we were just talking about before were things that were happening either at the surface of last scattering or prior to the surface of last scattering. But those photons still have to get to us. And when they do that, they have to travel through the universe as it's evolving over cosmic time. And so you take the map that is there, and as it passes through these structures, they will get slightly distorted. And those distortions will be a function of the when the structure was being formed and the magnitude of the structure. But what we see is that these distortions are predicted to happen on essentially 2-degree scales with about 2 to 3 arc-minute deviations in the pattern. Now, that wouldn't really be distinguishable from the original map itself. And you might be able to, if you squint your eyes, see this map flipping back and forth between a lensed and an unlensed map. But because these are happening on 2-degree scales, those scales are outside the event horizon at the surface of last scattering, meaning that the photons coming from one position and a photon coming from 2 degrees away from it on our sky couldn't have known about each other when they were emitted from the CMB. In other words, they were not in causal contact. So if I then take those photons and pass them by some large structure here, that photon can correlate them. They now know about each other, but via this massive structure in the middle. And so you're talking about looking for correlations on these scales, which then you can model and will tell you about where and when these massive structures are being formed. All right, and then from that you can get a power spectrum of that, and that's the lensing correlation function. So again, putting this in perspective, here's this no lensing temperature map. Down here is the E mode map, which again is predicted from the temperature map, and then here is a lensing B mode map, and then that's turning the lensing on and off, right? So here you have lensing and no lensing, and if you look at the scales here, you're seeing that to see that lensing signal, it's only 10% of the overall signal that you see in E mode. So again, you're just suppressing these things further and further down. They're becoming much more difficult to find. But because they have a B mode spectrum, they're uniquely distinguishable from the E mode spectrum in terms when you search for them. Now, another thing that's happening as things are forming, the structure is forming, is that the neutrinos, for example, or the light elements, light relics, I should say, are propagating through the universe. And if they have mass, they will tend to suppress the formation of structure here. These are just some pretty cartoons of dark matter and neutrino densities models. But over here you see what the effect of these things are. So here's the matter power spectrum over nothing going on. So if nothing's happening, it's just a flat line, which you see here. And as I start to add neutrino mass, you wind up starting to suppress the formation of structure. Now these scales here are large scales over here, smaller scales over here. Obviously, we've got a limit which is less than 1.2 eV, but this is just to show you as I start to add the mass, I start to suppress the structure. So finding the power spectrum of matter at different epochs in the universe, like the number of clusters and where they're located, and again how many of them and their masses, that will help you understand and constrain the neutrino mass. And then of course you can do the same thing with the lensing power spectrum. In other words, if I go back and measure the lensing power spectrum, I can actually derive the same kind of information. All right. So the clusters, which are again a tracer of matter, are something that I do a lot of work on. We find clusters of galaxies. These are objects which are 10 to the 14 solar masses, and they're the collections of hundreds of thousands of individual galaxies. Now, an individual star, of course, is not going to show up in our data, but a cluster, this happens to be the Coma cluster, let me just switch back here, is a rather large object on the sky. And inside that are a bunch of gas which has been stripped off of the individual galaxies which form the cluster. And because of virialized heating, those electrons wind up being very hot, in the order of 10 million degrees Kelvin. And because they're bouncing around in there, and they're moving at such velocity, they can actually leave an imprint on the cosmic microwave background. So as the CMB photons travel through, they'll get a boost in energy. We don't change the photon, we don't change the number of photons, but we boost the energy, the average energy of the photons. In temperature speak, what that means is that we take it from being a flat, just CMB spectrum, 2.73 Kelvin, and we remove photons at lower frequencies and we shift them up to higher frequencies over here, which gives you this classic Zanyaya-Zeldovich distortion spectrum. So when you scan across the sky at low frequencies, you wind up seeing a dearth of photons where there's a cluster, and so it looks cold at that one frequency. And at high frequencies, you see an excess of photons, so it looks hot, and you see these hot spots. And in this transition frequency, you don't see very much at all because it's on average the same. So you can use this to basically scan large patches of sky and look for a lot of clusters. Now, it doesn't do you much good to look at it at 270 gigahertz because there's lots of hot things in the sky, but it's a little difficult to make a cold spot in the sky against the CMB, and that's why this is such a powerful tool, which I'll show you in a minute. Again, these clusters are forming during with the mergers of objects. This is just a simulation showing you one of these mergers taking place. And as I go back in time, the merger history is such that you get these really large events happening, where this is the ratio of these two. This is like a 10-to-1 merger happening right here. And so these masses are really large. And so when these things come in from large distances, the amount of energy dissipated in these things is quite dramatic. You probably have heard of the bullet cluster. And the bullet cluster is sometimes called the second most energetic event in the history of the universe, second only to the Big Bang. So inherently interesting physical objects to study, independent of their tracers of mass for CMB, because dynamically and energetically they're just fascinating objects. So looking for these things, you might say, well, Planck has surveyed the whole sky. But Planck had a relatively small mirror, but good for a satellite, but not necessarily for looking for clusters. So its resolution was quite small. If you switch this and look at that was Planck. If you now look at ACT, it doesn't look much different, right? Because the CMB is a CMB. These are signal-dominated maps. But you can start to see, and you squint, you'll see little sources kick out here, and the ones which are red are going to be dusty star-forming galaxies probably, and so they're emitting in excess of photons in this case, the 150 gigahertz or the 2 millimeter band. So this is a little bit hard to do this with. So what you do is you just filter out the CMB to a cluster finder. CMB is noise, it's in the way. So you just get rid of all the CMB, you basically high pass filter the map, and it produces something which looks like this. And these bright spots with the dark rings about it, that's the ring is just a artifact of the filter. But the ones that are bright, again, are dusty star-forming galaxies. But if you squint your guys again, you'll see that there are a bunch of these cold spots in here. This map is a couple of years old. I'll show you a new one in a little bit. But the point is now you can go through and look for these cold spots and then identify the numbers of clusters. New data release, we have excess of, I think it's 9,000 clusters identified. So it's a vast improvement over this. When we first had our first data release, it was 35, right? So it's really satisfying to see this. And this is just a cool video showing us taking the ACT and combining it with the Planck maps and seeing this increase in resolution while maintaining these large scale signals. Okay, so what do you do with this? Well, I'll give you just two examples. One is you can just literally look for the most massive thing that you see in the sky. And obviously the bullet cluster is there, but then we found one called El Gordo, and is nice because of both because of its mass, which is 2 times 10 to the 15th, and its redshift, which is not, it's here is about 0.9, I think. So, or 0.85. So it's a really high mass cluster happening very early on, which means it's going to push the boundaries of having had enough time to actually form the object. And so you can compare an object like that over the area of the sky that we observed and see whether it's likely or unlikely to exist in a lambda CDM universe. And you can see in this case, it's right on the hairy edge of being unlikely, but certainly not anywhere near falsifying the existence. In other words, it could be a little bit more massive than this and still have, and just one of them on the sky. You couldn't have thousands of them on the sky, but having just one is not going to do much damage to the land of CDM. But eventually what you want to do is produce a plot like you see over here, where you have, again, the masses of these clusters versus redshift. And this is just a whole bunch of clusters from 2 different surveys, ACT and SPT. And you want to plot them there, and then you want to statistically understand how this is affecting your land of CDM. In other words, is this are these likely or unlikely? Now, I'm not going to go into it too much, but part of the problem with doing cosmology with clusters, especially large numbers of them like this, is the uncertainty in the mass of the clusters. It's difficult to get every mass measured individually, so you have to use something called the YM relationship, which just compares the strength of the signal that we see to the mass. And that typically has something like a 10% error. And that is dominating our ability to do cosmology with clusters in this form right now. So how do we do this? Many years ago, we built the Atacama Cosmology Telescope. Here's the team, a lot of people working on this to make it happen over many years. And this is just to give you an idea of the site. I hope that video is coming through. This is a flyover with a very expensive drone, no doubt. Flying over there I am right there, right down there. And so we've been developing this site since I started going there in 1998, I believe. And we've been pretty much going back ever since. And I'll show you a little while later, we're building the Simons Observatory. But it's a 6-meter diameter telescope. That's one of our students, Patty Ho. And this is the telescope. We're unloading the receiver here. So this is a pretty complicated piece of equipment that we've been, again, operating there in one form or another for ACT since 2006, I guess. So how do we do this? It really is actually, it still boggles my mind that we can get this done at all. Remember, we're looking at signals which in the primary CMB, we're looking at temperature fluctuations on the order of 120 microkelvin. But those primordial B modes are going to be in the 30 nanokelvin range. And you're looking at these photons coming here, but you're also looking at photons emitted from galactic dust, which are massively dominate the B mode spectrum. You're looking at photons which are coming from the atmosphere. You're looking at photons which are being scattered off your telescope into the receiver from the ground. And so this has 300 Kelvin emission, black body emission, which has to be suppressed literally by 11 orders of magnitude in order to be able to actually convincingly extract the kinds of signals we're looking for, which sounds like an almost unmanageable task. But we have techniques. One, of course, we don't want to get those photons in there, so we shield ourselves from them. The other is we can modulate the signal, and which only modulates polarization signals. So that'll suppress DC signals like from the atmosphere and much of what's coming from the ground. And then we can have multiple band instruments. In other words, these sources of emission from galactic dust and from synchrotron, they all have very well-known spectra. So if you measure your polarized signal in multiple bands, you can distinguish that signal from the thing that you're looking for, which might be a B mode signal, which has a different spectrum. And if you're in space, you can even add even more channels. So we built this telescope. The diameter of the telescope is designed to help us find clusters. And the sensitivity of the telescope, of course, is just to enhance our ability to be able to see primary CMB and also, as well as clusters. For this, we've built several receivers. We're in our 3rd generation receiver now. This is the 3rd generation one. And I'm not going to go into too much detail of it, but it uses a dilution refrigerator to cool the detectors to about 100 millikelvin. There are 3 different lens-based optics tubes in there, which have silicon lenses and a whole bunch of filters to suppress out-of-band signals into the system, and a Leo stop to help to control the illumination of the primary mirror, and then a detector array back up here, which I'll talk about in a second. We have, well, I'll get to that in a second. Just to put it in scale, again, the telescope here that's about 30 meters in diameter right there. The telescope itself is a 10-meter sized object, 15. The receiver is about 2 meters in size. The optics tubes are about 0.5 meter in diameter. And then we get to these arrays, which are just literally about 15 or 20 centimeters in diameter. And each one of those has a horn in it. And behind each horn is a are 4 detectors, 2 frequencies each, 90 and 150, for example, and 2 polarizations per frequency. And all that is read out by a series of multiplexing electronics over here, which goes out to the warm electronics on the outside of the receiver. And this has to go from 100 millikelvin here all the way out to 300 Kelvin over here. And it has to be held rigidly so it doesn't move around. So it's a challenge to make all that work. Again, just to give you an idea of what these detectors look like. Again, there's those 3 channels, MF 9150 and an HF 150-220. And actually now we just installed our LF band, which is at 20 gigahertz and up to 40. So, and then here's a picture of the cross slot antenna over here, and then here are the 4 detectors, 1, 2, 3, 4, and a series of band defining microstrip filters, which define the band even further, and the bands are defined down here. So pretty carefully designed experiment to put all this together, and we have about 3,000 detectors on a good day. So how do we do this? Well, we scan the sky. You know, this is a kind of an animation I literally made 15 years ago, but it still holds true. What you do is you basically scan back and forth in azimuth, and then you go to the other side of the south celestial pole and you scan back and forth in azimuth again, same piece of sky, but because of you're off the SCP, it winds up giving you a rotation of the scan, and what we call that is cross-linking. And the reason that's important to us is because the atmosphere itself, the DC emission from the atmosphere, will change because it's the clouds and everything up there, and you want to suppress that. And by cross-linking it, you're able to basically tell the code, look, you need to ignore things which for example, the sky outside the atmosphere must be the same where they're crossing, right? So you can fix the code such that it makes that true, which suppresses an enormous amount of low frequency noise that we get from atmospheric emission. In our maps for our most recent survey, our most recent release, we call the data release 4. There's a lot going on here, so I don't want to spend too much time on it. But you see the map coverages that we're talking about: deep 5.6, deep 8, and then this overall large survey, which you see around over here. So a big area covered, and then Boss North and so forth. So lots and lots of different areas that we've covered, both deep and wide. And this plot over here tries to summarize that, concentrating on the 150, this line right here. This is just the area of the map, and here's the depth that we have at that area. So 100 square degrees, we're going down to quite high sensitivity, I should say. And just to put that in perspective, we have 600 square degrees have less than 10 microkelvin arc minute noise on that, and for us that's about, I think, 3 times deeper than Planck all sky survey. So this kind of wedding cake depth pattern allows you to go again really deep and understand certain things about those small patches, but going really wide allows you to, if you're looking for clusters, for example, find that big one, but also for certain parameters that we're looking for example, and effective eventually for the Simon Observatory, really does require a large area of sky to beat down to get the sensitivity we need. So, and I'm gonna just skip that. So we're looking at the time stream from active course we started way back when, and the data we're talking about now is actually only through about 2017. And we have 2.5 more years data in the can right now. And in fact, the data we're taking right now is some of the best we've ever taken. In other words, the atmosphere the weather has really behaved quite well for us. And so there's a lot of new information here, but also a lot more, and a lot more coming. And the thing about it is that because these maps were really large, it was just an enormous influx of data that had to be dealt with, and techniques for analyzing it had to be developed. It took a little while, but now that's done. These newer data sets will start to roll out quicker. Again, this is one of our new maps. It's around 630 square degrees. Again, it doesn't look much different than other maps I've shown you, except it is getting more and more sensitive over larger pieces of the sky. And again, this map depth happens to be about 11 microkelvin. Now we can show you maps of Q that are signal dominated, and U, and you can see these classic QU patterns as I flip back and forth. And these are, these have signal in them, right? Those are signal dominated maps. And you can get to E, right, which is this E mode power spectrum. Remember, that's the one which is predicted from T, and it has to do with the Thompson scattering, surface of glass scattering. And then you can do B, and our B signal is clearly not showing up, and this is just a polarized, very bright source down over here. So we're making real maps with real sensitivity in them, and we now take those maps and we can do what we said we were going to do, which is to make power spectrum out of them and derive parameters. So this chart over here is just to say which one of the fields are being used to do this. These are the deep fields, and this is the derivation of TT, the temperature, the polarization power spectra. And then you can switch between that and the wide fields. And I'm only doing this because I'm going to show you some of our tests to make sure that our parameters are coming out right in a little bit. But you can see that the power spectra don't really change very much when you go between one or the other. The most dominant feature, of course, is this Poisson tail that we see here. This is coming from point sources, which are not cosmology. This is like dusty star-forming galaxies. And if you go deeper, you're going to see fewer of them, for example. So, all right. So now you take this and we put it all in one big plot here where we have, again, all the data with the TT, EE, and the B mode, and then the TE power spectra. And I plot everybody else's data on there. So this is now ACT alone, and this is ACT with SPT, polar barrier, and bicep Keck. And you can see that the story is not changing very much. People are getting, nobody's disagreeing with it or any great scale. So we're done with T, right? I mean, more sensitive is better, but I don't think anybody's in disagreement that we've done a pretty good job with that. E mode, again, is predicted from the T, and now we're starting to get these B mode spectrum coming in. Now, these are the lens B modes. This is not primordial. This is just coming from the gravitational lensing since the surface of glass scattering. So these are all very pretty, but what you need to do for them is to start extracting the cosmological parameters we were going for in the first place. So that happens by doing model fitting. And of course, I don't do that personally, but there's a whole bunch of people who do, and they're really good at it. And what they are really good at is doing it right and and trying not to make any mistakes. So this was a blinded analysis. In other words, they were given a random offsets to things, and they developed the code, and then they unblinded to see what they had. And so nobody was shooting for any particular parameter because they couldn't, because they were not provided with the information that would allow them to do that. And but even once they have the answer, they go and they do multiple checks, which is, for example, look at only the wide field, look at only the deep field, look at only one frequency, and derive the parameters, derive a power spectrum, and then fit the power spectrum to the model for any different way you can cut the data set up. And this is just showing you that you're looking for something which is dominating, which is saying, hey, everybody else is saying this, but this one piece of data is giving something which is distorting the results. And what you can see, that's not really happening here. I'm picking on H0 here because H0 is the parameter of interest of the year, I guess. People are really interested in that. And we'll come back to that in a minute. But of course, there's many more parameters than H0, and here they are, the ones I showed you listed up here. And we do these triangle plots to basically look for consistency to lambda CDN. And essentially, because one parameter might get you one answer, but they could making one parameter fit might come at the cost of making another parameter completely wacky. So you want to check them against each other to make sure that it's all self-consistent. And all of ours are pretty self-consistent. The one outlier is NS, but NS is really, it's the slope, basically tilt in the power spectrum. And our power spectrum is cut off here. We don't really go to these larger scales. And so we have a little less sensitivity there. And, or you might say we have sensitivity only on these scales. And maybe there's a break in NS. Maybe NS has a curvature to it. But right now, there is a slight inconsistency there. But for the most part, we are again, consistent with lambda CDN. Actually, for the overwhelming part, we're consistent with lambda CDM and with Planck and so forth. So getting back to H naught, here's our derived number from there, and this what we show here is there's the Planck number, which is in this light blue, the ACT plus W map, and then the ACT plus Planck. We won't care. Don't pay attention to the ACT plus Planck because Planck dominates there. But the ACT plus W map one is here, and you can see that it's obviously it's not improving on the error bar of Planck very much, but is very, very much consistent with the result from Planck. And is that an issue? Well, not really, unless you care about this plot, which is showing the status of the field in terms of measurements from cosmological kind of experiments like CMB experiments, where you see there's this consistently lower derived values of the H naught from the CMB experiment, and then there's this Cepheid work over here, which is showing something much higher, and then you have these other supernova giant branch ones, which are somewhere in between. And so we're not necessarily inconsistent with this work over here, but there's some serious tension going on with the Cepheid work over here. And hard to say right now to guess what's going on, but I would say there's a number of these. It's hard to imagine there's some kind of systematic going wrong with this many experiments to get the same answer all the time. So there would have to be something wrong with the model or something wrong. I doubt it's something wrong with the sky to show this is wrong. So the future is very bright for just ACT alone. Again, more data coming in, and we'll be releasing those hopefully on a regular basis on Lambda, which is run by NASA. So moving on, we never stop. A couple of years ago, the Simons Foundation, run by Jim Simons, gave us support for building a next generation CME instrument we're calling the Simons Observatory, co-located with ACT in the high Atacama Desert in Chile. And it's going to be bigger and better. I mean, the thing about these detectors is that we are built the detectors as sensitive as they can be from the ground. In other words, you can't make a more sensitive, you can make a more sensitive detector, but it will be dominated by noise from the emission of photons from our atmosphere. So the only way to get a more sensitive measurement of the CMB from the ground is to A, look for longer, or B, put more detectors in, or C, do both, and which is what we're going for, is number C, or letter C. And so what you see here is essentially the ACT receiver on steroids. It has the ability to have 13 of those optics tubes in it. The field of view has gone from 3 degrees up to 9 degrees, so almost a factor of 10 more throughput to the system. Again, a dilution refrigerator. But the really epic thing about this is that we're cooling 1,200 kilograms of material to 4 degrees above absolute zero, and about a couple hundred kilograms down to 1.1 degrees above absolute zero. So a technological feat, and if you don't mind saying so myself, to get this, to pull this all together. This is what it looks like in our lab at the University of Pennsylvania. This is the large telescope that we're putting it in, so it's a brand new telescope. It has to have an enormous secondary meter in order to help us produce that field of view. It's just a beautiful piece of equipment. It's being welded together now in Germany. This is the receiver. Again, you can see the average graduate student for scale. And this is 7 of the locations for the total of 13 optics tubes that can go into this system. It's actually pointed down right now. And realistically, in operation, it's always horizontal. So it doesn't really point. The telescope itself rotates around this axis right here. In addition to that, we have 3 small aperture telescopes, which look like this. Each one of those has a whole bunch of detectors in it. I can't remember off the top of my head, but a lot. And they are, again, located right next to this. And these are designed to go after B modes, right? So the large telescope is designed to go after lensing, clusters, the smaller scale science, and these small telescopes are going after strictly pretty much B modes. This is all located at our new site. Well, again, there's the ACT telescope, which I showed you earlier. COVID delayed us, but we hired ourselves our own hospital to go up to the site to help us manage testing of our employees. And so they're back up there plowing down the site, and they're going to construct our new buildings starting starting now. So that's also very exciting. In the end, we really hope to be making big strides on cosmological parameters, and this is just just a snapshot of that. But essentially, this is going to be getting down to, we hope, an R, which is the figure of merit for the gravitational B modes, down to 0.3 times 10 to the minus 3. We really hope to get down to 2 times 10 to the minus 3, which is a factor of 15 improvement over the current bicep limits. But then you can see a whole host of things where we're going to be doing massive improvements on the overall sensitivity. And this is the difference between when S4 gets built, they'll do even a factor of 4 better than SO, and so forth, and a factor of 2.5 better than us on other parameters. Then I promised I would give you an update on BLAST, which is a story in itself. I've probably spoken to some of you before about BLAST. It stands for the Balloon-Borne Large Aperture Submillimeter Telescope. This is a program that we've been running again since about 2002, with multiple flights from Sweden and Antarctica, our most recent one in last January. The purpose of this instrument is to look for polarized dust emission in the submillimeter, so at 250, 350, and 500 microns, and to use that as a probe for magnetic field strengths to try to understand the role that star formation plays in the evolution of in star formation in our galaxy, the rate at which stars form in our galaxy. And the short story is that when you look at star forming regions and you find where the matter is clumping, and you calculate the rate of star formation in our galaxy, you get a number which is somewhere like 10 or 15 times the actual rate that's measured. In other words, the predicted star formation rate is much less than the actual star formation rate, which means that something is keeping these clouds from collapsing. Now, that could be either some energy injection via turbulence, or it could be there's some kind of magnetic support or magnetic fields permeating those clouds. But if there's magnetic fields in the clouds, then they'll be aligning the dust grains, which are in the clouds, which are emitting light, and they emit in the submillimeter. So if we can look, and the dust grains are not, they're asymmetric, and so when they emit along their, and you align them along their long axis. When they emit polarized light. And so by measuring the polarized light, you can trace the magnetic field. And that's what we're all about. And we fly these things. Let me see if this works. I'm just going to show you my most recent disaster. Just really quickly, let me see if I can. If you've never seen a balloon launch, they're kind of fun. Yeah, I'm going to flip forward here. There we go, and one more time. There we go. Okay, so that's a balloon launch. Now that balloon will eventually grow into the size of about 28 million cubic feet, and all the material you see here is all balloon. And this expands by a factor of about 200 as it goes above most of the atmosphere. And that's a parachute. And that's it. But the thing you want to pay attention to is that thing up there. The thing that's holding that into that little tiny bubble is called the collar. The collar is think of it as a really, really heavy coat. And it's wrapped around the balloon material to keep the helium up in that bubble while it's being launched. And they have to let that collar go before they go up in the atmosphere. And you'll see this in a second. Here we go. Here we go. It's about to launch. Remember, that balloon's pulling up on that payload with about 10,000 pounds of force. And we let go. Okay, so watch carefully. All right, so now we launch. And now you see the collar falling, that little white thing. And bang. Oh, sorry about that if you heard that curse. All right, so it hit our telescope. And it put a big hole up here, which really wouldn't be too much of a problem. But it hit with the force that was really large. It was going really fast, I think about 60 miles an hour when it hit. and it damaged a carbon fiber tube that goes right across here, which is part of one of our structural components. So unfortunately, about 15 hours into the flight, there's the hole right there. About 15, here you can see it falling. There it is right there, and it fell a little bit more, it fell a little bit more, and then it wound up hitting right here. So it's going around 29 meters per second, 65 miles an hour or so. Did a lot of damage, and like I said, the whole thing failed about 15 hours in the flight, which is really disappointing because we were working on this telescope for a very long time. But ballooning is full of disappointments. But on the other hand, everything worked for that 15 hours. And so the detectors were working, the cryogenics were working beautifully. It was a crime to terminate the flight, but we had to. And we wound up, but it wound up falling on its head, and basically the camera blew up. So, which is a shame again, but you know, we did learn a lot about how the instrument works, and so being who we are, we said, well, let's do it again. We know how to make it work. Let's do it again. So we're now proposing what's called the BLAST Observatory, which is now designed to fly from Wanaka, New Zealand in 2026. It's a smaller mirror, but we are going to be operating at 3 frequencies starting at 175 microns, and then doing 250 and then 350 microns. So we gain back our resolution with that. Because we're flying mid-latitude, the sun sets, which is fantastic because it gives us access to the whole sky at night. We have many more targets to go after. We're switching to an off-axis design, which reduces the emission from the telescope by an enormous amount, and therefore the mapping speed of this is going just through the roof compared to the other ones. So essentially, we're applying all the lessons we learned from building the previous BLAST experiment to making something which is really going to be an immensely powerful piece of equipment. And the idea is to take, you know, these polarized maps from Planck, and then we can now probe them at 20 to 30 arc-second scales with our instrument to find the polarized fields there, and then you can go and look at them with different instruments with even finer resolution to really truly understand how these magnetic fields scale as we go further and further down into the star cores, into the small scales of the stars. And so we're going to be going from, prior to our 2009 flight, I think the number of polarization vectors measured were like this, you know, tens of polarization vectors measured on large clouds, to our BLAST flights, which were getting thousands, to now this BLAST flight, which is going to get millions. So several million polarization vectors, so a massive increase in the number in our information about these things. And this is just an example of our mapping speed relative to other instruments. And this is not to say that these other instruments aren't any good. It's just that for this particular science, being above the atmosphere is really an incredibly useful thing. So again, this is just showing that with an hour to get at our resolution, the ground-based instruments would be struggle to do that. But we're not going to be mapping the whole sky as some of these other instruments will be doing. We're going after very, very targeted regions. And then if you care about the regions we'll be looking at, we're going to be looking at molecular clouds, nearby molecular clouds, and some galactic plane surveys. But what's really interesting is that we are truly an observatory. So we're going to be devoting 25% of our time to shared risk observations, which will be managed through a proposal process. And so when this is done, we'll put out a call, and anybody who wants to go and use this instrument to look at their favorite object or study something can apply for time. And that's it. Thanks very much.
Okay, thanks, Mark, for a really wonderful talk. So we'll start the Q&A period now and do questions for the next couple minutes until the top of the hour. So a reminder to everybody to please submit your questions through the chat window. So, you know, go to the bottom of the Zoom panel and click on chat and then type your questions in there. And we already have one question, which is there a role for BLAST studying the transient sky during its 30-day observing?
Yeah, I am really into transients. Especially for ACT and Simon's Observatory, to tell you the truth. And it's a fascinating thing to look for. And, you know, there absolutely is, but remember the field of view of blast is quite small. I mean, it's less than a degree. So we can't go and get the sensitivity you would need on the kinds of timescales that are typical for transients, which would be a couple of days, and come back to it. Now, if there was a known, somebody, I guess we could become part one of the triggered observations. If somebody saw something, we could certainly slew to it at night and see the submillimeter, which is really an interesting thought.
Okay. So please do continue to type your questions in. I'll take this minute just to also announce that we have these webinars every month. We typically have them on the first Tuesday of every month at the same time, so 1 p.m. Eastern, 10 a.m. Pacific time. So our next one will be on October 6th, I believe. So please do join us in the future for those webinars. And Mike has a question, asks what the schedule for the BLAST Observatory is.
Well, we're not funded yet, so but currently we're applying for a Pioneers proposal, which is due in 3 weeks, which is why I'm sweating. But it's almost done. It's pretty much done, and that could start as early as February. But we're probably, if we get selected, we would probably start in about a year from now, and we would be flight ready 4 years after that.
Okay. And another question, is the BLAST Observatory planned to have multiple observing runs?
Yeah, well, you know, it hit me where I'm hurt the most. We would like to. If you fly over in Antarctica, you're pretty much always over the ice, and so the possibility for recovery is pretty high. The problem is Antarctica is a really hard place to recover from, so people have been having a harder and harder time getting their payloads back because of resource limits in Antarctica. But they do eventually come back. It takes a long time. There's this blue stuff on the other parts of the Earth called water, which is really bad for us. And so right now we are, one of the requirements for a Pioneer's superpressure balloon flight in mid-latitude is you count on not getting it back. That's not to say you won't, but what that means is that you have to find a different way of getting your data down. You can't count on recovering a hard drive, for example. And that opens up a whole interesting discussion, which I'd love to have with people, but essentially the TDRS satellite network has a certain bandwidth limit, which is where we normally get it down. But there's all these companies putting up these low Earth orbit satellites, which are going to mess with optical astronomers, but it'll be great for us because there's a lot of bandwidth. Now, Starlink doesn't go quite far enough south for us, but there's one called OpenWeb, I think, which is also launching satellites or something web. And so we really hope that by in 4 years that ugly satellite network will actually help us get our data down. And then we hope we fly over Australia or New Zealand towards the end of our flight, and or South America, and we can cut down in a place where we can recover it. Because it's a big investment in equipment, and it should come down fine, right? You should be able to recover it.
Yeah, and a comment from Doug Johnson is that protostars are turning out to be variable on timescales of a year or so, and the wavelengths of BLAST are optimal for those measurements for embedded sources.
Got it.
So another possible transient source.
But years, that's tough, yeah. Right? Because it's hard to get it up in the sky every year, right? I mean, and the cadence is pretty tough. It'd be interesting to know what the sensitivity numbers we would need to get for that. So, because if you could build a smaller instrument that could do it overnight, then you could fly whatever cadence you wanted from North America, and do something like that. So, if there was a science case for that, there is actually a lack of compelling science cases for North American flights, which would be less ambitious payloads. In other words, a North American flight's hopefully cheaper and faster, and you get them back and you can fly them again. And so that kind of science case, I think, would be well received. So if you want to contact one of us, let us know.
Yeah, I'd be curious about stellar flares as well, right? Because stars actually turned out to be quite active in the millimeter on, seconds to minute long timescales.
Right.
So a wide enough field of view, you sort of get potential for a lot of stellar flaring activity, science kind of by default.
Right, but again, we would need to know the kind of sensitivity levels we need to get to. In other words, we're a mapping experiment, right? So we can't put all of our power into a 2 arc minute by 2 arc minute field, right? The smallest field we can make is literally about a degree square, right? And so you have to take our sensitivity and you say that's the smallest map I can make, and what is the map sensitivity with that, and then you see whether it's relevant or not.
Yeah. Another question from Jens Kaufman is, do you ever look into the galactic plane with ACT?
You bet we do. We would like to avoid looking at that, but the Earth rotation is a real pain for us. So so we wind up going through the galactic plane as a matter of course. And in fact, when we do the Simons Observatory, we're going to be doing 40% of the sky, and we're going to have a huge galactic plane map. And we have a current map which is being looked at by number, but remember it's polarized map as well. So there's a lot of interesting stuff in there that people are starting to dig out. And all these maps are public, by the way, so it's on Lambda if people want to look at them.
Okay, great. So we're a little bit after noon, so I think we'll sort of end the Q&A period there. I want to thank everybody for joining us for our webinar today. Please do join us again in October. And we are always looking to solicit new speakers for our webinars. So if you would like to speak at a webinar or you think someone would be a great speaker, please send one of us on the Leadership Council an email. We especially invite suggestions for early career scientists of diverse backgrounds. And with that, I'll thank Mark again for a really excellent talk and everybody for joining us, and hope to see you in the future.
Bye-bye. Thanks.